Hi everyone, welcome to CAIE Science, and today we will be solving October-November 2022 variant 41 and 43 of 9701. Okay, basically 41 and 43 variants are the same variants. Okay. Question number 1. Potassium chloride and magnesium chloride are both ionic solids. Okay. Complete the energy cycle involving the enthalpy change of solution and lattice energy of potassium chloride and relevant enthalpy changes of hydration. Visual diagram. Okay, so in this question, you must remember the definitions of enthalpy change, lattice enthalpy, enthalpy change of solution, and enthalpy change of hydration. You must remember the definitions of these. So, what is the okay? Firstly, what is the definition of lattice energy? Okay, it is the energy change when 1 mole of ionic solid is formed from its gaseous ion. Okay, so this is ionic solid, and if gaseous ions, potassium ion gaseous, potassium ion, chloride gaseous, if they react together to form potassium chloride, so this is the enthalpy change of the lattice enthalpy. Sorry, okay, this is the lattice enthalpy. Now the enthalpy change of solution. So it is the enthalpy change when 1 mole of ionic solid dissolves in water to form infinite dilute solution. So when potassium chloride dissolves water, it dissociates into ions from ions, potassium ions and chloride ions in aqueous form. Okay. So this is the enthalpy change of solution. Okay. Now this is the enthalpy change of hydration. Okay. It is the enthalpy change when 1 mole of gaseous ion dissolves in water to form uh, infinite dilute solution. Okay. So this is your energy diagram. Okay. Moving towards next part B. Use the data in table 1.1 to calculate the enthalpy change of hydration of magnesium ion. So you are working. So in table 1.1, you are given the lattice enthalpy of magnesium chloride and enthalpy change of solution of magnesium chloride and standard enthalpy change of hydration of chloride ions. So you are given all of the energies which we need to calculate the enthalpy change of hydration of magnesium ions. So let's first construct a cycle. So cycle will be same like this cycle. Okay, like this cycle. So the magnesium 2 plus ions plus chloride ions, gaseous magnesium ions and gaseous chloride ions, they react to form magnesium chloride. So this is the enthalpy change of uh, lattice enthalpy. So this is the lattice enthalpy. So and it is a value of negative of 22493. Okay. Then you have magnesium 2 plus ions aqueous form, chloride ions in aqueous. So this is the enthalpy change of solution, and this is the hydration enthalpy change of hydration of magnesium ions, and this is the enthalpy change of hydration of magnesium ions. So now the your cycle is you can say cycle is completed. Now you just have to put the values. Okay, so this is the enthalpy change of solution of magnesium chloride, and you are given the value of enthalpy change of solution of magnesium chloride, which is negative of minus 155. Okay, now the enthalpy change hydration of chloride ions, it is negative of 364, but you will multiply it with by 2 because there are 2 moles of chlorides. Okay, 2 moles, and you have to find the value of magnesium enthalpy change of hydration of magnesium ions. Okay, so this is the x. So now this is this cycle. You will put the head to tail arrows on the one side of the equation, and the arrows which don't follow this trend will be on the other side. Okay, so this negative of, okay, let's first So negative of 2493 and negative of 155 is equals to x plus negative of 364 multiplied by 2. Okay. So now your equation is created, and from here you will calculate the value of x, and which is going to be the enthalpy change of hydration of magnesium ions, and which is negative of 1920, okay, kilojoules per mole. So this is your final answer. Okay, moving towards next part. C. Explain the reasons why the lattice energy of magnesium chloride is more exothermic than the lattice energy of potassium chloride. So if you see in the periodic table, this um, this is the magnesium and this is potassium. Okay, you can see that there are more shells in potassium because potassium is in fourth period. Okay, 1, 2, 3, 4. Potassium is in fourth period and magnesium is in third period, so it will have three shells of electrons. So this magnesium will have a less, uh, you can say, more charge density. Okay, and this potassium will have less charge density because there are more shells, so there will be more shielding factor, and magnesium is similar. Okay, so magnesium has a greater charge density, that's why this has more lattice energy. Okay, so magnesium 2 plus has greater charge density or greater charge density. Okay, you can write that greater charge than potassium and is smaller than K plus. Okay, so greater attractions between magnesium 2 plus and Cl negative chloride ions then yes, you can write this. Okay, then the attractions between potassium ions and chloride ions. Okay, so you can write that magnesium is has a greater charge density. Okay, that's why this is greater attractions between magnesium ions and chloride ions than the attractions between potassium ions and chloride ions. Okay, part D. Define the following terms: enthalpy change of atomization. So it is the enthalpy change when one mole of gaseous atoms formed from its elements. Okay, so it is the enthalpy change when one mole of gaseous atom is formed is gaseous atoms gaseous atoms gaseous atoms formed gaseous atoms formed from the element. Okay, so this is the definition of enthalpy change of atomization. Now the first electron affinity. So it is the enthalpy change when one mole of gaseous atoms gain one mole of electron. Okay, uh, when atoms gain electrons they form anions, so this is the electron affinity. Okay, when one mole of gaseous atom um, gains one mole of electrons. Okay, so enthalpy change when one mole of gaseous atoms form 1 mole of electrons. Okay, now moving towards next part. Explain what is mean by entropy. Okay, so entropy is actually a measure of disorder, or it also has a different definition, which is number of possible arrangements of particles and their energies in a system. Okay, so number of possible arrangement of particles and their energies energy in a system. Okay, so this is the entropy. Okay, now potassium chloride is very soluble in water at 20 degrees Celsius. Okay, explain the solubility of potassium chloride by reference to the entropy. Okay, so when potassium chloride dissolves in water, it forms potassium ions plus potassium ions plus chloride ions, like this. So solid is converted into liquid, so the entropy increases. Okay, so that's why enthalpy change is positive, or entropy change is positive. Entropy change is positive because ionic ionic lattice ionic solid or lattice ionic lattice solid forms aqueous ions. Okay, so now you have to understand that the entropy of solids is lesser than liquids, and the gas has largest entropy. Okay, so that's why uh, this entropy, when the solid is changed into liquid aqueous, so the entropy will increase. Okay, now pen tab is not working. I Okay, moving towards next part 3. Use the Gibbs equation and your answer to E1 to predict whether the potassium chloride is more soluble in water at 20 degrees Celsius or at 80 degrees Celsius. Okay. So the equation, Gibbs free equation, is in this: enthalpy change negative temperature and enthalpy change multiplied by entropy change. So you know that from the part E2, that the entropy change is positive. Okay, because solid is converted into liquid. Now you have to see what is the enthalpy change. So this is the when this is actually the when potassium chloride is dissolved, this form is when potassium chloride dissolves, it forms potassium aqueous plus ions plus chloride ions. So you can see that this is actually the enthalpy change of solution of potassium chloride, and you are given the value of enthalpy change of potassium chloride. Okay, enthalpy change of solution of potassium chloride. So this is plus 15. Okay, so now the enthalpy change is plus 15. So this is also positive. So this is positive and this is also positive. Okay, but when this Gibbs free energy is negative, then the reaction is more feasible. Okay, so now if you you have to tell that whether Gibbs free energy is more negative at T 20 degrees Celsius or 80 degrees Celsius. Okay. So if you see, if the temperature is 80 degrees Celsius, okay, so this value will be, this all value will be more negative. Okay. So this value will be more negative. So the Gibbs free energy will be more negative at higher temperature. Okay. You can see that from the equation. Okay, because the enthalpy change of solution is also a positive. Okay. So when the temperature increases, this factor becomes more negative, this factor. Okay, so the Gibbs free energy will be more negative. Okay, so the potassium chloride will be more soluble at 80 degrees. Okay, so more soluble at 80 degrees Celsius because Gibbs free energy is more negative at higher temperature, higher T. Okay, moving towards next question. Question number 2. Explain what is meant by the following terms: homogeneous catalyst and heterogeneous catalyst. Okay, so homogeneous catalyst is the catalyst which is in the same phase as the reactants, and heterogeneous catalyst is in different phase to reactants. Okay, so catalyst in same phase, in same phase or state, same phase as reactants. Okay, and this heterogeneous catalyst is catalyst in different phase to reactants. Okay, so these are the definitions of homogeneous and heterogeneous catalysts. You have to remember them. Okay, now iodide ions react with peroxy disulfide ions. Okay, this reaction is slow, but it is catalyzed by Fe2 plus ions. Okay, write two equations to explain how this reaction is catalyzed by Fe2 plus ions. So this Fe2 plus ion actually react with firstly this peroxy disulfide ions. You can see that this 2 plus will change into then 3 plus ion 3 plus. Okay, St S2O8 2 minus. So it will form Fe3 plus plus 2SO4 2 minus. Okay, you have to balance the equation as well. Okay, so now you have iron 3 plus, and this iron 3 plus will react with iodide ions to form iodine plus Fe2 plus. Okay, um, balance the equation. Okay, like this. Okay, so you can see that in the end Fe2 plus ions are unchanged, so it is behaving as catalyst. Okay, this Fe3 plus ions actually react with iodide ions to oxidize iodide ions to iodine, and they themselves reduce to Fe2 plus ions. Okay, so these are the equations. Okay, suggest why the alternative route in the presence of Fe2 plus ions has a lower activation energy than the route in the absence of catalyst. So in the absence of catalyst, you can see that these both ions are negatively charged, so they will repel each other. They are both anions, so they will repel each other. But when Fe2 plus is positive, is present, this Fe2 plus is positive. Okay, so when this first react with peroxy disulfide ions. This is negative, so positive plus negative, they will attract each other. So that's why the activation energy will be lower in the presence of Fe2 plus ion. Okay, so reactants are both negatively charged, or anions negatively charged, so they repel each other. They repel each other. Okay, moving towards next part. Nitrogen monoxide reacts with oxygen. Okay, this reaction is a second order with respect to nitrogen monoxide and first order with respect to oxygen. Okay, under certain conditions, the value of rate constant K is 8.6 into 10 to the power 6. Okay, construct the rate equation for this reaction. So in rate reaction, the concentrations of the reactants are involved. So in this description, it told you that this reaction is second order with respect to nitrogen monoxide. Concentration of nitrogen monoxide, there will be K will be here. Okay, and this nitrogen monoxide, the reaction is second order with respect to nitrogen monoxide, so it will have uh, a power of 2. Okay. Then you have this oxygen, and the order of reaction is first order with respect to oxygen. So concentration of oxygen. So this is your rate equation. Okay. Now calculate the initial rate of the reaction under these conditions when the initial concentrations of nitrogen monoxide and the initial concentrations of oxygen is this. Okay, initial rate. So you are given this equation, you just have to put the values. So rate is equals to K is given to you, which is 8.6. This is K, 8.6 into 10 to the power 6 multiplied by what is the concentration of this nitrogen monoxide, which is 7.2 into 10 to the power minus 4 cube square multiplied by oxygen 1.9 into 10 to the power minus 3. So rate is going to be 8.47 into 10 to the power minus 3. Okay, this is rate 8.4 into 10 to the power minus. Okay, moving towards next part, part C. Okay, the drug cisplatin hydrolysis in water. Okay, the rate equation is shown. Okay, so the rate is first order with respect to this cisplatin. Okay, the value of K is 2.5 into 10 to the power minus 5. Okay, under certain conditions. This reaction has a constant half-life. Okay, explain why this is the case, why this is a constant half-life, because you can see that the overall reaction is first order. Okay, the overall reaction is first order. Okay, so the half-life of first order reaction is constant. Okay, now moving towards next part, use the information in this question to show that the half-life of this reaction is 2.77 into 10 to the power 4. So for the first order reaction, the half-life is a formula of 0.693 divided by K. This is the formula for the to calculate the half-life for the uh, first order reaction. You have to remember these formulas of half-life. Okay, so 0.693 divided by K. You are given the value of K, which is 2.5 into 10 to the power minus 5. So you will get the answer of 2.77 into 10 to power 4. Okay, hence shown. Okay, now 8.8 into 10 to power minus 6 moles of cisplatin are added to 100 cm cube of water. Calculate the time taken for the concentration of cisplatin to fall to this 2.5 into 10 to the power minus 6. So firstly, let's calculate the initial concentration. So initial concentration is equals to mole divided by volume. So mole are given to you 8 into 10 to the power minus 6 divided by this is 100, but you have to divide it by 1000 to make it into dm cube. So this 1000 will move upwards, so this will be uh, 8 into 10 to the power minus 5, okay, mole per dm cube, mole per dm cube. This is your initial concentration. Okay, now the formula is new amount. You have to remember this formula. New amount is equals to initial amount divided by 2n, and where n is number of half lives. Okay, you have to calculate the number of half lives. Okay, so the initial amount, so let's put, take 2n to the uh, this side. Okay, 2n is equals to initial amount is 8 into 10 to the power minus 5 divided by 2.5 into 10 to the power minus, so you will get an answer of 30 here. Okay, so 2n is equals to 32, and this 32 is actually 2 into 10 to the power 5. Okay, you can see, so n is equals to 5, so it means 5 half lives are passed. Okay, so the time taken will be 5 into half life. What is the half life? This is 2.77 into 10 to the power 4. Okay, so the half life is constant, and 5 half lives are passed. Okay, so the total time taken will be 1.39 into 10 to the power 5. Okay, 1.39 into 10 to the power 5. This is one method, and you can also find a different method in marking scheme as well, but I thought this method would help you a lot. Okay, you just have to remember this formula. New amount is equals to initial amount divided by 2n, where n is number of half lives. I hope you understand this question. Okay, moving forward, question number 3. Data should be selected from table 3.1 in order to answer some part of this question. Okay, now part A. Standard electrode potentials are measured under standard conditions. Describe the standard conditions. So in this cell, half cell, so standard conditions are 1 mole per dm cube, and the temperature should be room temperature. Okay, room temperature. So the concentration of this 2 tin 4 plus, and these ions of tin must be 1 mole per dm cube. Okay, mole per dm cube, and 298 Kelvin. Okay, this is the room temperature. Now moving forward, complete the diagram below to show the the electrode potential can to show how electrode potential of this half cell can be measured experimentally. Okay. Use diagram. Your diagram should be fully labeled to identify all the apparatus. Okay, so you have to draw the diagram for the electrode potential. Okay, standard electrode potential, and for electrode potential, the other half cell will be a hydrogen. Okay, because hydrogen is a standard cell. Okay, so let's draw the diagram. Okay, so but the you can see that there are only ions in this solution. Okay, so there will be platinum. Firstly, let's make this as a solution of half cell of SN2 plus. Okay, so this is platinum, platinum, and you have in solution ions of tin 4 plus and 2 plus. Okay, these ions of tin. Now this is going to be the hydrogen half cell. Sorry, this is that's so this is going to be the hydrogen half cell. This is also platinum, and you will have this kind of delivery. This will be like this. We will have a voltmeter over here, and the hydrogen gas will enter the apparatus from here. Okay, so hydrogen gas. Okay, and there will also be a salt bridge like this. Sorry, my drawing is not accurate, but things are understandable. Okay, this is salt bridge. Okay, and in this solution you have ions of H plus ions, aqueous H. Okay, okay. So this is your complete diagram. Okay, I hope you have understood everything, and this voltmeter will give you the reading of electrode potential. Okay, this will give you, because hydrogen has the electrode potential of 0 0. Okay, now moving towards next part 3. Equal volumes of 1 mole of this tin 2 plus and 1 mole of chloride are mixed. Okay, use the relevant electrode values to explain whether the reaction occurs between these two ions. Okay, so SN2 plus and chloride ions. So these are your chloride ions, and this is SN2 plus, because these chloride ions will oxidize into chlorine, and this you can say will reduce. Okay, this chlorine will oxidize. So let's first write the equation. Okay, SN2 plus Cl, when they both react, they will form actually SN plus chlorine. Okay, like this. So you can see that this tin is reduced and chloride ions are oxidized. Okay, and the half cells of these two are shown to you, but you can see that and this is a reduction, this is reduction, and this is oxidation. Okay, and each cell is going to be E reduction minus E oxidation. So now let's calculate the E cell. So E reduction is the one which is reduced, which is 10. Okay. So what is the reduction potential, which is negative of 0.14. Then you have the oxidation. Okay. And this is the oxidation potential 1.36. Okay. So in total, you have a half cell 1.5, which is negative. So the reaction will not happen because uh, half cell should be the cell, electrode cell, E cell should be positive. Sorry, E cell should be positive. Okay, but here the E cell is negative, so no reaction will happen. Okay, so no reaction because the E cell is negative. Okay, E cell is 1 - 1.5 volts. Okay, so the reaction will not happen. Okay, you also have to show the working. E cell is equals to negative of 0.14 negative minus plus 1.36. The answer is okay. Now let's move to the next part. Equal volumes of 1 mole of SN2 plus and acidified 1 mole per dm cube of this ion are mixed. Write an equation for the reaction that takes place. So SN2 plus. So this could be this SN2 plus, and you have this ion. Okay, VO2 plus. This is this ion VO2 plus. You also have VO2 plus ion here. So which of these equation you will use? Okay, so you will use the equation which will have more reduction potential than the reduction potential of this half cell, because this is oxidized, so this will reduce. Okay, so this will be the equation. Okay, because in this equation this VO2 plus ions are oxidized, but they have to be reduced to V3 plus ions. So these both are will be the equations. Okay, so if you write the SN2 plus, so this equation will be flipped. Okay, because this is now oxidized, so SN2 plus will become SN4 plus 2 electrons, and this VO2 plus 2 H plus electron, 1 electron, it will become V3 plus water. Okay, and you have to balance the electrons, so multiply this equation with 2, so you will have 2 moles of VO2 plus 4H plus 2 electrons, and this is, so now cancel out the electrons from both sides, so the final equation will be SN2 plus 2VO plus 4H plus. So you will have SN4 plus, that's 2V3 minus plus water. So this is your final equation. Okay, so you have to write the equation. Okay, write an equation for the reaction that takes place. So the final equation was SN2 plus 2VO2 plus signs, SN2 plus 2VO2 plus ions plus 4H plus ions. Okay, that become SN4 plus um, this. Okay. So this becomes V3 plus water. Balance this. Okay. So this is your final equation. Okay, for the reaction. Now moving towards next part B. A solution of tin chloride is electrolyzed for a measured time using a steady current. Okay. The mass of 2.95 gram of tin metal is produced at cathode. Okay. Aluminum oxide is electrolyzed for the same time by the same current. Okay. Calculate the mass of aluminum metal produced at cathode. Okay. Give your answer to three significant figures. So if this SN2 plus signs, okay, in this, what is the formula? What is the oxidation state of aluminum in this? Which is aluminum L2 3 plus. Okay, aluminum, and this tin has charge of 2 plus. Oxidation state of tin is. So when the tin is formed at cathode, what will be the reaction? This tin will gain 2 electrons in 2 plus, so it will form tin metal. And what will be the equation for the cathode reaction of this aluminum? So it will gain 3 electrons, aluminum. So it will form aluminum solid. Okay, to balance, you have to balance the electrons. So let's balance the electrons. You will have these equations. 3 moles of Sn2 plus 6 electrons, so 3Sn, 2L2 plus 6 electrons, and 2 moles of aluminum. Okay, so these are your equations. Okay, so let's now let's calculate. Now the equations are ready, so let's do calculations. Okay, the mass of the tin metal produced at cathode is given to you. So let's change this into moles. Okay, so moles of tin that will form is equals to 2.95 divided by AR. AR of tin is, you can see from periodic table, which is 118.7. This periodic table, where is SN? This is your tin. Okay, so 118.7. Okay, this is your AR. So from here you will calculate the moles of Sn. So you will get an answer of 0.0249 moles. Okay, now you have to calculate the moles of aluminum that will form by ratio. So you can see the ratio from these equations. So 3 moles of uh, the ratio is 3:2. Okay, so when 3 moles of this tin are formed, 2 moles of aluminum are formed. Okay, so when 0.0249 moles of tin are formed, how many moles of aluminum will form? X is going to be 2 into 0.2 upon 3 multiplied by 0.0249. Okay, so you will get the value of X, number of moles of this aluminum. Okay, so this will be 0.0166 moles. Okay, now you are given the moles are calculated. So now what it asks you in the question, calculate the mass of aluminum. So mass is going to be moles multiplied by mr. So what is the mr of aluminum? Let's see from this, well, which is 27. Okay, so 27 is the mr. So the final answer, the mass of chlorine, mass of aluminum that will produce at cathode is going to be 0.448 grams. Okay, 0.448 grams. Okay, this is your final answer. Moving towards question number 4. Okay, a sample of butanoic acid is shaken with a mixture of two immiscible solvents, ethoxyethane and water. Okay, the solvent forms two layers. The butanoic acid is distributed between the two layers. Okay, its concentration in ethoxyethane being higher than its concentration in water. State what is meant by partition coefficient. So it is the ratio of concentration of the solute in two solvents, in two immiscible solvents at equilibrium. Okay, now part 2, the partition coefficient for the butanoic acid between ethoxyethane and water is 3.5. Okay, a solution of 2 gram of butanoic acid in 100 cm3 of ethoxyethane is added to water. This mixture is left until there is no further change in concentration of butanoic acid in either solvent. Mass of butanoic acid dissolved in ethoxyethane layer is now 1.65. So what will be the mass in this water layer? So mass in water layer will be 2 minus 1.65. So the mass in water layer will be 0.38 grams. Okay. Now you have to calculate the volume of water which is used. Okay, so the formula for the KPC is this formula. KPC is concentration of X in, let's say, an organic compound, organic solvent, and in water. So the KPC value is given to you, which is 3.5. And what is the concentration of this butanoic acid in the ethoxyethane? So concentration is going to be 1.6 divided by 100. Okay, and what will be the concentration in water? So in water it will be 0.38 divided by X, and X is the volume of water used, and you will calculate the volume of water from this X. So now the equation is ready. You will calculate the value of X, and X will be 8.82 cm. This is your final answer, 82 cm. Okay, moving towards next part. An aqueous solution of butanoic acid can be used to make a buffer solution. So what is the buffer solution? This is the solution which resists change in pH when small amount of acid or base is added. Acid or base is added. Okay, now moving towards next part. Suggest one organic compound and one inorganic compound that can be added to two different samples of aqueous butanoic acid to produce a buffer solution. So buffer solutions are of two types: the weak acid and salt of weak acid with strong base, and the other is weak base and salt of weak base with strong acid. Okay, so we have this buffer solution. The weak acid is given to you, which is butanoic acid. Okay, this is butanoic acid. Now the salt of this weak acid. So the organic compound will be this, the salt of weak acid. So this will be a salt of butanoic acid. So you can say sodium butanate. Okay, you can say that, and that sodium butanate will have this ion CH2, CH2, and COO. Okay, you can write this as well, and or you can write sodium butanoate. Okay, and the strong base will be like inorganic compound, which will be sodium hydroxide, NaOH. Okay, so that's how you will complete this part. Part C. The solubility of aluminum hydroxide in water is 2.47 into 10 to power minus 9. Okay, give the expression for the solubility Ksp of this aluminum hydroxide, sorry. So when aluminum hydroxide dissolves in water, this forms aluminum ions plus hydroxide ions. Okay, so the definition of Ksp is the product of concentration of ions of sparingly soluble salt. Okay, so the concentrations of product of ions, so it will be concentration of Al2 plus 3 plus, sorry, and concentration of hydroxide ions, and there will be a Q because the moles will be in the power in the K equations. Okay, Ksp. Now calculate the numerical value of Ksp of aluminum hydroxide. Okay, include the units of Ksp in your answer. So when this aluminum hydroxide, let's write this equation again. Aluminum hydroxide. Okay, when this dissolves, it forms aluminum to 3 plus ions and OH ions. So let's say if X concentration of aluminum hydroxide is dissolved, so X moles of this aluminum 3 plus ions will form, and 3x moles of this OH ions will form. Okay, so here you are giving the concentration, which is 2.47 into 10 to the power minus 9. Okay, so in Ksp, though, so the when the concentration of aluminum hydroxide is 2.47, so the aluminum of the concentration of aluminum 3 plus ions which will form will also be the concentration of aluminum 2 plus ion 3 plus ions will be 2.47 into 10 to the power minus 9. Okay, and the concentration of this OH ions will be 3 into 10 to 3 into 2.47 into 10 to the power minus 9, and in power there will be a 2. Okay, so from here you will get the value of Ksp. Okay, and that is 1.01 into 10 to the power minus 33. Okay, 1.01 into 10 to the power minus 33. And what will be the units? Units will be, you can see, mole per dm cube multiplied by mole per dm cube, and the power is cube. Okay, so it will be mole power 4 and dm cube minus 12. So this is your final answer. Okay, moving towards next question. Question number 5. A transition element is a d block element which forms one or more stable ions with incomplete d orbital. Okay, two of the three orbitals are dxy orbital and dz orbital. is the shapes of these orbitals. The shape of dz is unique, all like this. Okay. So now the shape of dx. So firstly, you will just draw the two axes. This is, let's say, y-axis, and this is x-axis. So the xy orbital will be in between uh, these two axes. Okay. So now you know that how to draw this xy. Let's draw this. Okay. So this will be like this. Okay. This will be like this. You don't have to consider the z orbital, z axis over here. Okay. Now part B. The nickel 2 plus ion forms many complexes. A solution of containing this complex ions of nickel is green. Okay. When an excess of 1,2-diaminoethane (EN) is added, the color of the solution changes to blue. This is due to the formation of this complex ion. Okay. Explain why the two solutions are colored and why the colors are different. Okay. So why the complex form colored? Because there is a D-splitting when the complex forms. Okay. So D-splitting occurs. Okay. In complex, D d orbital d splitting or d orbital splitting occurs. Okay. D splitting occurs. So and electrons and electrons are excited, and they and the photon and the wavelength of visible light is observed, and the wavelength of this visible light is absorbed, and the color seen is complementary. Okay. the, the electrons are excited, and wavelength of visible light is absorbed. Okay. So complementary color is seen. Okay. That's why the transition elements are colored. So the D splitting occurs. Okay. Like this. So this energy gap, that's so this is the energy gap between these two energy, these splitting. Okay. This is the energy gap. Okay. So and a photon uh, absorbs a specific frequency or wavelength of visible light, and the rest of the color, the rest of the energy gives a complementary color. Okay. And why they have a different colors? Because this energy change could be different, and or the frequency of wavelength which is absorbed could be different. Okay. So they have different colors because um, energy gap is different. Okay. Energy gap is different, or you can also write that the wavelength absorbed is different. Okay. Or different frequency or different wavelength of uh, light is absorbed. Okay. Moving forward, the nickel En3 complex can exist as a mixture of two stereoisomerisms. Okay. Complete the diagram Complete the three-dimensional diagram to show the one of the stereoisomerism. Okay. Each En ligand could be represented using this symbol. Okay, so this En is bidentate ligand. Okay, so it will form one molecule of this En will form two dative bonds. So there are three Ens. So in total they will form six bonds. So the geometry will be octahedral. Okay, like this, and you have to show this En with this symbol. Okay, so this is your first stereoisomerism, and the second will be the mirror image of this isomerism because they are optical isomers. Okay, now the name the geometry of the complex sign drawn in B2. So I already told you this is octahedral. Okay, and the type of stereoisomerism. So the type of stereoisomerism is optical. Okay, now part C. Iron to carbonate and nickel to carbonate both decompose when heated. Okay, iron to carbonate decomposes at a lower temperature than nickel carbonate. Okay, suggests a possible reason for this difference. Okay, so it is possible that why this iron to carbonate decomposes at lower temperature, because uh, this iron could be smaller. So when the anion is smaller, this cation, sorry, when the cation is smaller, there is more polarization of anion, so the bond is weakened. Okay, so it is possible that this iron is smaller or nickel is bigger. Okay, you can write from any of this. So let's say iron Fe2 plus is smaller. Okay, or has greater charge density. You can also write this. Okay, so there is more polarization of anion, or you can say carbonate ion. Okay, that's why they this this Fe2 plus this iron 2 carbonate will be require less energy. That's why it requires less energy. Okay, because due to polarization, this iron 2 carbonate, this attraction between this iron to carbonate will decrease. Okay, so it will require a lower temperature, or you can uh, write the opposite one for the nickel carbonate. Okay, so this is the possible reaction. These reasons are similar to the stability of the the compounds down the group. Okay, you can remember that. Okay, now moving forward, part D. A is a pale green salt containing Fe2 plus ions. Sample of 2.62 gram of A is dissolved in water, and a solution is made up to exactly 100 cm cube with water. A 25 cm cube of sample of this solution. Okay, 25 cm cube of samples of this solution are placed in conical flask and titrated against 0.01 mole per dm cube of acidified potassium manganate 7. The equation for the only reaction that occurs is shown. The average titrate is 335 cm cube. Okay. Describe the color change that is seen in the conical flask at the end of the titration. So you know that these Fe2 plus ions are green, but when you acidify them, they become colorless. Okay, so the initial color will be colorless, or you can also write green as well. Okay, and when this MnO4 is added, so the final color will be pink. Okay, now calculate the percentage by mass of iron in A. So you will first calculate the now you are given the concentration and volume of potassium magnet. Okay, so let's find the moles of MnO4 first. Moles of MnO4, which is going to be N is equals to Cv. So concentration is 0.01 into 35, but you will divide it by 1000 because you have to convert it into dm cube. Okay, so this will be a 3.5 into 10 to the power minus 4 moles. And from the ratio, from the equation, you will calculate the moles of iron Fe2 plus Fe2 plus and 25 cm cube. Okay, and 25 cm is equals to 3.5 into 10 to the power minus 4 multiplied by 5. Why 5? Because in equation you can see that the ratio is 5:1. Okay, when 1 mole of MnO reacts with 5 moles of Fe2 plus. Okay, so the moles of Fe2 plus ions in 25 cm cube will be 1.75 into 10 to the power minus 3 moles. Now the moles of this Fe2 plus ions in 100 cm cube. Okay, because we use 25 cm cube sample. Now what would the moles, what will be the moles in 100 cm cube? Okay, so the moles of Fe2 plus in 100 cm will be you will multiply it by 4. 1.75 into 10 to the power minus 3 multiplied by 4. So this will be 7.00 into 10 to the power minus 3 moles. Okay, so now you will calculate the mass of iron. Mass of iron is equals to 7 into 10 to the power minus 3 multiplied by this mr 55.8. So you will get the answer of 0.3906 grams. Okay, because you have to calculate the percentage of iron in A. So the mass of iron in A is this, and the mass of A we used is 2.62 grams. Okay, so from here you can calculate the percentage by mass of iron in this sample A. 0.3906 divided by 2.62 into 10 to the power into 100, sorry, into 100. So from here you will get the answer of 14.9%. 14.9. So I think that's all for the day. We will do next questions in the next part. Okay, I hope everything is clear to now, and if you have any questions you can ask me in the comments. Thank you everyone for watching, and see you soon in the next part.